Today's lecture would be on basics of materials and energy balance, and if the time permits, I will introduce to introduction to metal extraction. That is where we will be doing material and energy balance in various processes. You know that materials and energy balance are the routine plant exercise. It is nothing new that I have to tell you, because every businessman or every shopkeeper or every plant owner, he has to do a sort of auditing of material and energy from the point of view of the economics. He would like to know what are the inputs, what are the outputs of material, and where are the losses. He would also like to know what is the energy input into the system and what is the energy output, so that he can assess the energy consumption, because energy consumption, it acts directly to the cost of the product. Probably he would like to measure the saving of energy or utilization of energy, if he happens to know how the energy is being utilized. So, let us see first of all what are the basics of materials and energy balance. I mean, it is nothing very great, it is very simple. You know that you also do a sort of balance whenever you go to the market and do some expenditure. You are given 100 rupees, when you come back you will like to know how you have spent 100 rupees. So, you keep an account of input and output, so that you can introduce the measure of saving, if at all it is possible. Now, something like similar is also here, that is, now you have to think in terms of inputs and output of material and energy. Now, in fact, the basic is, it is based on law of conservation of mass. Law of conservation of mass. Now, mass of an isolated system, it remains constant, irrespective of the changes occurring within the system. Now, let us consider an open system, for example. Consider an open system say at this point, this is point 1 and this point 2, here we have input and at point 2 we have output. Now, here let us consider the volume is V. Now, mass is transferred into and out of the system. Mass will accumulate when the input and output rates are unequal. So, in this case we can write down rate of mass in, rate of mass in that is equal to rate of mass out, rate of mass out plus rate of accumulation of mass, accumulation of mass. It is very simple. Now, just writing down in terms of mathematical expression, if m is the mass dm by dt, that will be equal to m dot in minus m dot out. Dot represents the rate of change of mass with reference to time. So, this is in fact valid for unsteady state operation. Unsteady state operation. Now, this material balance equation is written for each and every component of the system. Suppose in a system there are 10 different elements are entering or 5 different elements are entering. and 5 different elements or 10 different elements are leaving the system, then we have to write down the mass balance for each and every component that is entering in. For example, say if we have component 1 dm1 upon dt, that will be equal to m dot 1 in minus m dot 1 out. Similarly, for example, for component 2, we will write dm2 upon dt, that will be equal to m2 dot in minus m2 dot out. So on, I can write down for third component dm3 upon dt, that will be equal to m3 dot in minus m3 dot out, and so on. Say for ith component, that becomes dmi upon dt, that is equal to m dot I in minus m dot I out. Now, say for a system with multiple inputs and output streams, the material balance equation for ith component, that becomes dmi upon dt, that is equal to sigma mi in all components minus sigma m dot out of, let us say, all components. This is again for all components. Say for ith component, that is what it means. Now, if we have for a steady state, now as the name suggests, there is no accumulation of mass within the system. Therefore, sigma m dot I in, that will be equal to sigma m dot I out. That is the basis of the when the system is in steady state. Now, for a chemically reacting system, in addition to the law of conservation of mass, the following two laws must also hold. First is law of definite proportions. Law of definite proportions. Now, a given chemical compound always contains the same constitutional elements in the same weight proportions. Now, this is only true for stoichiometric compounds. For non-stoichiometric compounds, this may not hold good. For example, FeO, it has Fe1 and O1 atom. It is also available Fe 0.950. So, in that case, this law of definite proportion will not be valid. So, I will just write down a given chemical compound, always contains the same constitutional elements, in the same weight proportion. That is important. In the same weight proportion. For example, Fe2O3, there will be 2 atoms of iron combining with 3 atoms of oxygen. And for Cu2S, 2 atoms of copper combining with 1 atom of sulfur. However, here copper and sulfur, they are the same constitutional elements, but Cus is also formed. So, that in that case it will not valid. So, that means this is true for stoichiometric compound. True for stoichiometric compound. For non-stoichiometric compound, you have to find out in what proportion the elements are combined. Second important law is that law of multiple proportions. Law of multiple proportions. Now, this law states if 2 elements can form more than one compound, I repeat once again, if 2 elements can form more than one compound, then the respective weights of one element that combines with a given weight of the other are in the ratio of small whole numbers. I think I should write for you, say if 2 elements can form more than one compound, then the respective weights of one element that combine with other are in the ratio of small whole numbers, or in the ratio of small whole numbers. So, you will very often come across the various compounds, stoichiometric as well as non-stoichiometric in nature. In case of stoichiometric compounds, the combination of elements is clear, but in case of non-stoichiometric compound, you must know in what proportion the elements are combined. So, then and then you can perform the material balance. Now, this is the I mean these basic, though I said, I think all of you are be aware that input should be equal to output when there is a steady state. That is a very simple thing. Now, say about the energy balance, basic thing about the energy balance. Now, one important thing for energy balance is energy balance cannot be done without material balance. That is, whenever you are required to solve a problem of energy balance, without performing material balance, energy balance cannot be done. So, that is one important thing. Now, here some tips. For example, one can perform elemental balance either in kg or kg mole. Now, it is a matter of practice and matter of convenience how you perform the material balance. You can perform in kg also, or in gram also, or in gram mole also, or in kg mole also. If you ask me, I will prefer, or I do the material balance by considering kg mole, because I find very convenient by determining the input and output of masses in terms of kg mole, because later on the thermodynamic values which I will be getting in the literature, they are given per kg mole. Also they are given per kg, also they are given, but I find it more convenient. So, what I wanted to say is that you have to develop your own habit, whether kg is suitable for you or kg mole is suitable for you. The thermodynamic values are available in kg as well as in kg mole, gram as well as in gram mole, there is no problem at all, but it is just a matter of convenience. How also the material balance in kg mole, it becomes little bit easier. Say if you write down the stoichiometry equations, then immediately it is apparent how many moles are entering in and how many moles are entering out. So, I find it little easier, but then as said, you have to make your own style of solving these problems. Once you have done the material balance of all inputs, that is, here it is very important to know that the input of materials where it is going in. Say you have x kg or x kg mole of certain material is in, you have to see how much of that is going into the products. The products could be metal, it could be slag, it could be waste product, or it could be in the gaseous form. So, you have to collect all such information, make a box to determine the material balance, and then proceed to solve the heat balance. That is very important. And another important thing for the energy balance is to make a basis of calculation. Well, the basis of calculation you have already made, say while doing material balance, for example 1 kg mole, then you follow that kg mole till the end of your heat balance, or you can do 100 kg mole or 10 kg mole, whatever is convenient to you, but then do not change the basis till the end of the problem. Number 2, the several energy balance, it is done by considering a reference temperature of 298 Kelvin. Now, this is an advantage, because the values or the thermodynamic values like specific heat, heat content, heat of reaction, heat of formation, they are all available at 298 Kelvin. Well, it is again a matter of practice. Now, once you have done this, then perform heat balance. Then perform heat balance. Now, needless to mention, heat input that is equal to heat output, because we are talking of a steady state. We are not performing heat balance under unsteady state. We can also perform under unsteady state, in that we know what is the accumulation of energy in the system. But normally, or in most of the plants, it is required the the plant is operating at a steady state for days together, inputs and output of energy and so on. So, you perform the heat balance, it is very simple, heat input is equal to heat output, though it looks to be simple, but here you have to consider all sources from which heat is entering. So, I write few sources for you, for example, heat input. Say heat input, you have to consider heat input by chemical reaction. You have to see whether in a system chemical reaction is occurring. Now, I have already illustrated how to calculate the heat of reaction when I was discussing thermochemistry, and there we have calculated also. So, here it is important to calculate the heat of reaction because of the chemical reaction, that could be exothermic also, that could be endothermic also. So, accordingly, the sign convention you must be very clear, say exothermic is a negative if you want to do that, or endothermic positive, or you declare in the beginning that this is what the convention I am going to follow, but then you stick to the convention, that is an important thing. Now, here again the temperature is also very important. You have to see that whether the products, whether the reactants, they are entering at what temperature and products are at what temperature. So, accordingly heat of reaction has to be calculated as per the formula which I have given in thermochemistry, that is the heat of reaction at 298 plus heat of reaction at the prevailing temperature. There you have to do these proper calculations are very important. Then the next step is that you collect the thermodynamic data. This is the most important step while performing the heat balance, because you have to know from where which data will be available. Though while going through the problems over here, I will give you the data, I will give you the source, but then in an unknown situation, if you are required to do heat balance, you must know how to collect the data, and if in certain cases the data may not be available, then you should be able to derive the data from basic thermodynamics. That is important. So, collect the thermodynamic data, collect the thermodynamic data on Cp, that is the specific heat, it is available kilocalorie per kg mole per degree Celsius, or joule or kilojoule per kg mole per degree Kelvin per degree Celsius per kilogram. All these values are available, but then follow a certain system of collection of the data in proper units, so that you do not end up in a problem. Also collect the data on heat of formation, say heat of formation of compounds, heat of formation of compounds. Normally these heat of formation of compound, they are available at 298 Kelvin. Now here also you should know the state of elements or compound, state of elements oblique compounds. Do you know why I am telling this thing? Because if there is a transformation in the solid phase, I mean there could be transformation within the solid phase and transformation on melting and boiling. So, at all these transformations there does not occur temperature change, but latent heat you have to consider. So, it is with this context, it is important to know the state of element or compound when you attempt to make a heat balance of a particular problem. So, if it is a mere say solid state transformation, then you have to know at what temperature the transformation is occurring from say alpha to beta, within what range, then accordingly you have to use the Cp value in that range. Then you should also know the melting point. Then the important thing over here to know the latent heats. Why I have written is simply because many times I have seen in performing heat balance, we might forget latent heat, but well there is no reason of forgetting. So, latent heat, now this latent heat could be for transformation either in the solid state transformation or in the liquid transformation, say from solid to liquid and liquid to gas. At each stage you have to see what is the latent heat. Also heat input could be say a sort of combustion energy. Combustion energy. Now, this if fuel is used as a heat source. Now, if you use fuel as a heat source, then two things you must know. Number one, what is the chemical composition? Number two, what is the heat of formation, or what is the calorific value of the fuel, and what is the energy it is being released on combustion. So, this is the combustion energy. Also, many a times in many processes you will find that the reactants are heated. Say for example, in various high temperature processes, sometimes air is heated, sometimes the reactants in general they are heated. So, you must also know what is the sensible heat of reactants, sensible heat of reactants. Now, with that I mean you have to calculate sensible heat, but to calculate that you must know what is the temperature at which the reactants are entering. That is an important thing. Now, some terms for heat output. Heat output. Now, you have to see in what stream heat is being taken out. It may be taken out say solid products, Then for solid products, you must know Cp of all components, And here also, because they are solid, if there is a phase transformation in the solid in that temperature range, then probably it is also important to know the latent heats. B is there a liquid product. Now, in solid products you also require to know what is the temperature. In liquid products you have to know what is the temperature, whether the liquid product which is exiting the system, it is at the melting point or is above the melting point. Then these are the important issues. Here temperature of each component, because you have to see how many products are forming, temperature of each product, composition of each product, Cp value of each product. Then you should also know the heating value, or so to say heat content at that particular temperature, latent heat if you are calculating from 298 degree 298 Kelvin. Then heat of mixing. If you recall in the lecture on thermodynamics, I said various heat input, various heat output terms heat of mixing, because when a liquid solution forms, say for example, if silicon dissolves in iron, there is the heat of solution or there is the heat of mixing. Similarly, the two oxides that dissolve, in certain cases heat is generated. So, that heat of mixing should be known. We should also know where heat of mixing is produced, by addition of which oxide to which oxide heat of mixing will be available. So, that information must be known in order to come to an exact or accurate heat balance. Now, C important is the gaseous product. Now, normally in almost all metal extraction processes to which we are concerned, the output is solid products, liquid products or gaseous product, or combination of all the three or two, or whichever is done. So, for the gaseous product, again here you require to calculate how much heat is being taken out. Needless to mention, you require the value of Cp. Now, here I would like to tell one important thing here, that many students I found they do the mistake, not by that they are not knowing, but they are not cautious enough. Say heat content in water, when you want to calculate, say heat content in water. So, for calculating this you have to consider these steps, probably it will help. Say H2O liquid at 25 degree Celsius, that is equal to H2O liquid at 100 degree Celsius. You should know the Cp value of that. Then H2O liquid at 100 degree Celsius, that is equal to H2O vapor at 100 degree Celsius. Here what you should know, there is a transformation. So, you must know here latent heat. You must know the latent heat. Third, say H2O vapor at 100 degree Celsius to H2O vapor at the temperature, you must know again the value of Cp. That is here important, because the Cp is also a function of temperature. So, accordingly you must collect the important values, and many times a mistake occurs in calculating the heat content in water. Suppose a water or the water vapor is being discharged at, for example, 1400 degree Celsius, then if you select the state of water as liquid, then you have to calculate the heat content, say first of all you bring vapor from that temperature to 100, latent heat will be evolved, then from liquid to 25 degrees. So, what I mean, these are the things that you must consider. Another important D is calculation of heat losses. Now, heat losses are very important feature and they are integral part of the high temperature extraction processes, and you must be able to calculate heat losses. Now, here the mechanism is very clear, that is the conduction, convection and radiation. So, invoking the appropriate laws and the method of calculation, you should be able to calculate heat losses, because these heat losses, if they are in very large amount, then one should think of how to minimize these heat losses to conserve the amount of energy. So, with this, say a slight basics of materials and energy balance, I will again say it is just a sort of a common sense. If I summarize what I said till now, I will say it is just a common sense. Every day your dad must be giving 100 rupees, and at night he must be asking, well, what is your balance? So, you must be able to tell him, Dad, you gave me 100 rupees in the morning, now I am left with the 5 rupees, immediately he will ask you, where did you spend, give me the balance. Same thing here, your plant manager has given you, for example, 100 tons of raw material, and he wants to give, and he wants to know what are the outputs, so that his objective is to minimize the losses if at all they are occurring. That is all the whole objective of this material and heat balance exercise. Now, let us now apply to these concept to actual metal extraction processes. Now, before we go that, a brief account of the metal extraction process is very much desirable, because without this you may not be able to understand how to apply these balances. So, with this I will give you a brief introduction to metal extraction. Now, first thing I will like to say, what are the sources of metals? Sources of metals. Remember, metals occur in the nature as minerals. Metal in the nature does not occur as metal. That is a very, very important thing that you must know. So, there are two sources, one is the primary source. Primary source, you have natural reserves. Natural reserves. As I said, metals are in form of minerals, oxides or sulfides. It is important to know what is a mineral, because there is often, when a question is asked, what is the difference between mineral and ore. So, I found many students, they sometimes confuse. So, I should be very clear, a mineral is an inorganic compound in which elements are combined in stoichiometric proportions. That should be very, very clear. I repeat again, a mineral is an inorganic compound in which elements are combined in stoichiometric proportions. So, the natural occurrence of metal is mineral, and as I said, it is an inorganic compound. For example, I take Fe2O3, 2 molecules of iron are combined with 1.5 molecules of oxygen. That is, here the ratio of Fe upon O2, that is equal to 2 upon 1.5. Take SiO2, 1 molecule of silicon is combined with 1 molecule of oxygen. Similarly, we take Fe3O4. The ratio, for example, if I write Fe upon O2, that will be 3/2. Let us take Al2O3. The ratio of aluminum upon O2, that will be equal to 2 upon 1.5. That is what the meaning of mineral is. The elements are combined in mixed proportions. Another source is secondary. In the secondary resources is scrap or recycled products, But the amount of metal or the amount of consumption of metal with which we are concerned is enormous, is in the million tons. Hardly the secondary resources can meet the requirement of a very large requirement of the human beings. Therefore, the main resource or source of metal is the primary reserves. So, I will write the heading natural with which we are concerned, natural reserve or reserves of any metal that is called, write with a different ink, ore. So, remember there is a difference between ore and a mineral. A mineral is an inorganic compound in which elements are combined in a stoichiometric proportions, whereas an ore is an aggregate of minerals. Remember, ore in fact is an aggregate of minerals. Aggregate of minerals. That means what? That means an ore of a metal, it will consist of valuable mineral, and plus all other is called gangue minerals, What does a valuable mineral means? Say a valuable mineral is one in which we are interested in the production of metal. For example, let me give you an example. For example, I consider here metal, name of the ore, constituent of the ore, constituents of the ore, valuable mineral, and gangue mineral. Now, gangue mineral, gangue it is called because it is a vest. Now, remember when I say it is a vest, it is vest with reference to the metal in which I am interested in production. Otherwise, gangue it is also a mineral. So, remember when I say it is a gangue is a vest, I am meaning that for production of that particular metal, rest all is a vest with reference to that particular metal. So, for example, I take metal as iron. The name of the ore is hematite. Now, hematite contains Fe2O3, SiO2, Al2O3, P2O5, etc., etc., etc. Now, here the valuable mineral, because we are interested in iron, so valuable mineral is Fe2O3, and all other, for example, SiO2, Al2O3, P2O5 are considered to be gangue, but they are also mineral because SiO2 one molecule of silicon and 2 atoms of oxygen. So, silicon is also a metal which is a very important metal. Al2O3, aluminum is also a metal, remember. Similarly, another example magnetite. Here I have constituents are Fe3O4, SiO2, it can have Al2O3, it can have P2O5, it can also have TiO2 and etc., etc., etc. The valuable mineral is Fe3O4 and rest all say SiO2, Al2O3, P2O5 and TiO2, etc. all other are the gangue minerals. Another example I take aluminum. The name of the ore is bauxite. Now, bauxite has Al2O3 into XH2O, it has Fe2O3, it has TiO2, it has SiO2, etc., etc. Now, here in this aggregate of mineral which is called an ore, the valuable one is only Al2O3. Rest all say H2O, Fe2O3, TiO2 and SiO2 are gangue minerals. Another example I take zinc, sphalerite is the name of the ore. Sphalerite may contain zinc sulphide, lead sulphide, Cu2s, SiO2, Al2O3 and etc., etc., because you do not know what the nature has stored for you. Here the valuable mineral, because I want to get only zinc, so zinc sulphide, and with reference to this PbS, Cu2s, SiO2, Al2O3 are gangue mineral, though Pb is also a metal that can also be recovered from the gangue depending upon its concentration. Similarly, if I take an example, I can take number of examples. Titanium, ilmenite is the ore, ilmenite. Composition you have Fe, TiO3, you have SiO2, MgO, etc. Now, here the valuable mineral is titanium dioxide. Rest say FeO, SiO2, MgO, they are all gangue minerals. Now, another important metal is copper. Copper name is chalcopyrite, and chalcopyrite, the constituents are CuFeS2, it could have SiO2, it could have Al2O3, it could have Fe2O3, it can also have calcium oxide, etc., etc. Now, here the valuable mineral is only CuFeS2 and all other, for example, FeS or FeS2, SiO2 or Al2O3, they are all considered to be the gangue minerals. So, what we note from here, that ore being an aggregate of minerals, we must know what is the quantity of metal that in ore has. So, that quantity is quantified by defining metal grade. Metal grade of an ore that indicates ore value. Now, as I said, if the metal grade is high, then the gangue mineral is low, and accordingly less effort has to be done for removal of the gangue. So, metal grade is a very important issue. Now, how to define metal grade? Metal grade that is equal to amount of metal upon amount of ore. Amount of ore, if I want to define metal grade in a ore. Now, for example, I can also define metal grade of a pure mineral. In that case, I have to take amount of metal in the mineral upon amount of mineral. Now, for example, I take pure mineral, say pure mineral, let us define the metal grade. For example, I take Fe2O3, then iron grade in pure Fe2O3, that will be equal to 112 into 100 upon 160, and that makes 70%. What does it mean? 30% is a waste that has to be removed if you want to get iron. Now, for example, if hematite, which is an ore, it contains 80% Fe2O3, then the metal grade of ore, metal grade or iron grade of ore, that is equal to 56%. What does it mean? 44% is the gangue, and that has to be removed if you are processing the natural reserve, which is hematite. That is an important. Now, let me give another example. Let us consider a mineral for copper, which is a CuFeS2. Now, let us find out the copper grade. Copper grade in CuFeS2, pure mineral, that will be equal to 64 upon 184 into 100, that is equal to 34.78%. Now, see, the copper grade in pure CuFeS2 is 34.78%. Now, imagine if copper ore has 20 to 30% CuFeS2, which is normally the case, could be even less than that. The content of CuFeS2 could 20 to 30% or could be even less than that. In that case, the copper grade in ore, that will be 7 to 10%. What does this mean? That means, out of every 100 kilogram of ore, you have only 7 or to 10 kilogram of copper. Rest is gangue, or rest you can call is a waste with reference to the copper, and they have to be removed. So, that is an important thing that you must understand from here. Now, similarly, say nickel grade, which is again an important strategic metal, say nickel grade in nickel ore, it also varies, for your information, though it will depend upon location to location, it varies between 2 to 5%. Right. So, it is accordingly the amount of waste that you are producing from the synthesis or from the processing of the natural reserves of this metal is enormous. For nickel, having only 5% nickel, I mean 95% is a waste. And remember, these things are also, they are not physically separable, they are chemically combined. For example, the hematite ore, it has Fe2O3, chalcopyrite, it has CuFeS2. So, here copper and sulfur, they are not physically combined, my dear friend, they are chemically combined. Similarly, Fe2O3, iron and oxygen, they are chemically combined. You cannot just do by breaking and removing sulfur from copper or removing oxygen from iron, it is not possible. So, what I mean, they are also chemically combined. So, what we can say from here, if you are looking from extraction of metal from natural reserves, what has to be done? What are the basics? So, the extraction of metal, from natural reserves no doubt we are going to use ore. So, what we have to do? First step that you have to see, removal of oxygen, or sulfur From where? From valuable mineral, because we are interested, for example, in ore of iron, we are interested in iron and nothing else. From valuable mineral, this is the first step that you have to do. Removal of oxygen or sulfur from the valuable mineral, that is the first step in processing the natural reserve in order to get the metal. Second important step is separation of metal, from the gangue minerals, from the gangue. Now, remember here separation, though it might convey to you it is a physical, no, it is not that physical. I mean, it may require certain reaction and so on, but the separation I mean that once you have got or once you have gotten the oxygen or sulfur removed from the valuable mineral, then you have in aggregate metal plus gangue. Now, you have to separate it. Again, you cannot separate it chemically, you cannot separate it physically. So, these are the two steps that are required to extract metal from natural reserves. And what are the techniques? The techniques of metal extraction. Whatever technique you adopt, these two are the important steps. First technique is pyrometallurgy. The term pyro means high temperature, that means here the temperature or thermal energy dependent. This pyrometallurgical route is thermal energy dependent. So, that is where energy balance is an important issue, thermal energy dependent. Second is hydrometallurgy route. Hydrometallurgy, it is not thermal energy dependent, but it requires a very enormous amount of liquids, mostly water. And third, though it is not an independent route, but it is combined with hydrometallurgy, that is the electrometallurgy. That is the electrometallurgy route. Now, these are the three techniques which can be used to extract metal from the natural reserves. So, the following unit processes are used. Following are unit processes. In case of pyrometallurgical extraction, pyromet I am writing short form, first step is roasting, second step is smelting, it is called either as a matte smelting or reduction smelting. Third step is converting, and fourth step is refining. We will take these in our subsequent lectures along with the material and energy balance. For hydrometallurgy, the various unit processes are: one is the leaching, and second is the separation of metal from aqueous solution. Separation of metal from aqueous solution, because hydrometallurgy you have the metal in the solution. Now, here various techniques are used. One is the cementation, then you have aqueous solution reduction, then you have electrolysis, and then you have solvent extraction technique. Now, some example, for example, copper by pyrometallurgical route, it uses roasting plus matte smelting plus converting plus refining, combines all of them. I give 1 or 2 example. I take for example zinc, it combines roasting, reduction smelting, plus refining. See, if you take for example pig iron, it has reduction smelting. These are the combination of unit process to produce the metal. Say steel, reduction smelting plus refining. So, this is in short the various processes that are used.